Okay, so let's have a look in our booklets now. Why do we need to do quantitative calculations? Well, we need to know if something's going to run out before, like if I've got two reagents together, which one's going to run out first? Or if I know that I want to make 10 grams of a product of, say, iron, well then how much iron oxide do I need to start with in order to get that amount at the end of the reaction? And so we're going to look to see how chemical formulae and equations can help us work out how much we either need or how much we're going to produce. And when we're looking at how much, then it's called stoichiometry. You don't need to use this word in any of your assignments or things like that, but if you see it, you need to not freak out. Gee, that's a random, weird-looking word. I don't know what it means. So this is all to do with chemical quantities. Okay, and you might remember from Criterion 4 that we were interested in the relative atomic mass of elements, and we found them on the periodic table. Do you remember what the relative atomic mass is? What does that mean? Maybe talk, yeah?
Isn't it something to do with the percent abundance in nature?
Percent? Yep.
Something about relative to carbon 12 atoms in it? Of 1/12 of the carbon 12 atom?
That is it, exactly. So there's two things that we need to remember about relative atomic mass. The first one is that it's the percent abundance in nature. It's like a weighted average. And it's relative to the mass of 1/12 of the mass of the carbon 12 atom. That's it precisely. So the mass of any element is made up of protons, neutrons, and electrons, but the mass of electrons is so small that it really is negligible. So what we're interested in when we're working out the mass of an atom of an element is the number of protons and neutrons that it has. Now, if I have just one atom, and if I think about this is my nucleus, this could be boron 10, because I've got 10 protons and neutrons in the nucleus. So that would be 5 protons and 5 neutrons in the nucleus, add up to give me 10 of the particles in the nucleus. And it doesn't matter whether it's a proton or a neutron, the mass is essentially the same. So what would I call this? What do I call this particular one? If I've just got one atom, and I know how many protons and neutrons it has, it is an element, but it's also an isotope. because I know exactly how many neutrons I have in this atom. And it could also be boron 12, say. What's going to be in the nucleus of a boron 12 atom?
5 protons and 7 neutrons.
And this is another isotope of boron. Yeah, because it's the same element, because it has the same number of protons, but it has differing numbers of neutrons. And the percentage that these occur in nature then, the relative abundances, is then going to influence what the final relative atomic mass for boron is. Okay, so that's just a bit of a reminder from Criterion 4. But we do need to know what we're talking about when we use the symbol for an element. What does that actually mean? Now you've got a little image on page 13 there showing you that 3 helium atoms have the same mass as 1 carbon atom, because helium has 2 protons and 2 neutrons in its nucleus, and whereas the carbon-12 has those 12 subatomic particles. 4 times 3 is 12. So 3 helium atoms is the equivalent of 1 carbon atom. And we can also look at it the other way, that the titanium has the same mass as 4 carbon atoms. So its mass must be 48. Now, at the moment, when we're saying 48 for the titanium, we know that this means protons and neutrons. But we haven't really talked too much about how we're going to actually weigh them. Because weighing protons and neutrons, that's because they're very, very tiny. They don't weigh very much at all. These are going to be hard to measure, aren't they, in the context of a chemistry lab. So what we need is an easy way where we can use this information to help us figure out quantities that are actually going to be useful in everyday chemistry. Okay, so we look here on page 14. We've got a calculation for the relative atomic mass of chlorine. We're told that 75% abundance of chlorine 35 and 25% for chlorine 37. And hopefully you remember, again this is a calculation from Criterion 4, that in order to calculate the relative atomic mass of chlorine, we would need to find 75% of 35 and add it to 25% of 37, and we end up with 35.45 as the average, the weighted average. Do you remember doing these calculations? Okay, so now, again, though, we're just talking about, we can use, we can use AMU as the units for talking about atomic mass units. But again, we're still not at the stage yet where we can use this to for our chemical reactions. Hopefully, with that bit of background, we can work from there. That if this is how we can work out basically the number of protons and neutrons in an element, we're going to use the same process to work out what's present in compounds. So if we have water, and I want you to use this method for your calculations. Just use the masses on your formula sheets. So if you look up the mass for hydrogen, you'll see it's 1.008. So just use that number. And in water there are 2 of them, so I'll multiply that by 2. And then there's 1 oxygen that has a mass of 16. It's then going to give me a total mass of 18.02. Relative molecular mass now. Yep, so straight from the formula sheet. Nitrogen dioxide. What's the bonding present in nitrogen dioxide? Covalent. Is it going to be a molecule or a network? A molecule. Okay, so I look up my nitrogen, and then there are 2 oxygen atoms, and then I add them together. Sulfuric acid. Okay, so essentially all we've done here with our relative molecular mass is add up all of the protons and neutrons that are present for all of the elements in those compounds, because the electrons don't really give us, contribute anything significant to the mass. So, if we want to calculate the relative molecular mass of sugar, C12H22O11, then we're going to look up on our periodic table what's the mass for each of these elements, and then we multiply how many we have by the mass of 1. And just add them all together. Alright, is that okay? Making sense so far? No questions? There are some questions for you to do, or the relative formula mass. It's all the same process. Actually, what we might do the worked example together on page 16, and then I'll get you to go back and read through the pages that we've skipped. So for calcium phosphate, if we're just given the word, what kind of bonding firstly in calcium phosphate? Ionic. Why is it ionic?
Because calcium's a metal.
Calcium's a metal. So then when we're working out our balancing, this was done for you, how do I know that I need to balance this way? That is, I'm going to look up the charges that would form on these ions on my common ions table. What charge does calcium form? 2 plus. It forms 2 plus because where is it on the periodic table? It's in group 2. What about the phosphate ion? What's its charge? -3. Yep. And so when we look at how we're going to combine these together so that we have no net charge, I need 3 of these. To balance out the charges. Because this is a complex ion, I'm going to need to put a bracket around it to keep those numbers separate. So this is what I have in here, which means that when I'm working out the quantities, I'm going to need 3 lots of calcium. Got 2 phosphoruses. Now the way the worked example has it, just putting the bracket around everything, which is fine, but I'm going to do it the other way. You can see here I've got 4 times 2 is 8 oxygens. And hopefully that is clear over here as well. I've got 4 oxygens plus 4 oxygens is 8 oxygens. Okay. So it doesn't matter either way, it's fine, either in the brackets or as separate calculations. But we must realise that this 2 means I've got 2 phosphoruses, and then 4 times 2 is 8 oxygens. Right, let's have a go at doing some calculations for our compounds.